Okay, so we want to continue, and the next part of the work, we are supposed to conduct a mass and energy balance and specify the product stream and the cost utility of the plant. So I won't spend too much time on this one because the main focus is on the optimization part, right? But just briefly, if we want to determine the or do the mass and energy balance, right? We have finished our flow sheet, everything is fine. What we can do is that coming. Okay, so from the home tab here, we can see over here we have summary. So there's model summary, stream summary, utility cost, all these things. Now for the mass and energy balance, if we click on the drop down for stream summary, we can tell Aspen that we want a summary for all the streams. So if we should click on that, it's going to give us every single stream and its properties, values, anything at all we are looking for. Okay, now if we don't want it for everything, but we want it for just the boundary, so the inlets and the outlets, right? What I mean by that is just these ones, they are coming in, but they don't have a place they are coming from. So we just have these ones here, and these ones are coming out, but they don't have a specific place they are going to, or a specific unit they are going to. These ones don't have a specific unit they are coming from, so they are the boundary streams. If I should click on them, I'll get the properties for those streams. I can do it for the feeds or for material I'm charging into the system, or for just products, right? So for certain groups that I specify. Now for material balance, we need to do it for everything. So the way we used to go about it is we select all. When we have this, we copy the data. So we used to take temperature. I can press Control, select pressure. I can scroll down. I'll make mass flow active, click Control, and then select all these ones, or maybe mass fractions, the one whichever one you want to use. Then I can click Control C and then paste it in Excel. So then I know the values for all the streams. Then when I'm done, I look at, okay, if I pick the first units, maybe mixer one, which streams are going to mixer one? Feed, recycle, and gas recycle. So those become the inlets to that stream. Then mixer, the outlets becomes just one. So I can draw a block and then do the inlets to that and then the outlets from that. So oh, where are the results? Where are the results? The results are not showing here. Okay, no problem. Let me just do it again. Oh, we did it for B. Okay, that's fine. So these are the results that you would have, right? So we have the values for all the streams. So the mass balance is a bit time consuming. You have to consider every stream coming to every unit and leaving every unit. But you can also look up here. You would see where it is coming from over here and where it is going to down here. So you can use that as well to know what to do. Right, then for the energy balance, we do the same thing, but on this time, instead of us picking the mass flows or the mass fractions, we pick the enthalpies. So I used to pick the molar enthalpy. So that's here. I used to pick the molar enthalpy, and then I multiply them by the mole fraction, so that I get the enthalpy for each species in the stream. So that's how we used to do it. So maybe I pick the enthalpy for this stream, that's minus 14399.8. Then I come here to mole fraction and I pick this value. So I multiply this by that to get the enthalpy for just toluene in that stream. I multiply this by that value to get the enthalpy for hydrogen in that stream. So that's what we do. So we get the enthalpies for every component in every stream, and then we can take it from there. Now the question mentioned that we should specify the product stream and then the cost utility. So the product stream, we can just go and pick the values from the product stream and look at the masses and then the energy there, right? For the cost utility, then what we are looking at is we are looking at how much energy is going to the total heating and then the total cooling. So we can use the relation this is from thermodynamics, right? We can use the relation K plus W is equal to M change in H, and then we can find all the work done by the pumps, the compressors, all of those things. We can find the change in enthalpies, and we can find what the Q is supposed to be, or we can just find all the Q values by checking all the streams. So maybe I'll come to heat X, I right click on results, I look for the heat duty, so that's down here. So I can pick the heat duty, so that's going to be the Q for heat X. Then I come to maybe another unit, so maybe the cooler, do the same thing, pick the Q. So that's the heat duty. Yes, I pick the value. So I add all of them up. That will give me the utility, right? The energy of the utility for the plant. Okay. Now let's look at how we can do the optimization part. It says that we should determine the optimum flash temperature in order to maximize the plant's profit. Now they've been given the equation for the profit, so it's P prod of Benz P minus C cooler times absolute value of the cooler duty. Um, if we or if we continue reading, it tells us that the P prod is the price of the product, so that's giving us 1.2 pound mole. C cooler is the cost of cooling, so that's 10 to the power minus 4 BTU per hour. And then we're told that the Benz P is the mole flow of benzene in the product stream, and KO cool is the cooling duty of the cooler block. Okay, so for us to work with optimization or sensitivity, right, either optimization or sensitivity, we come to the navigation pane here and we look for model analysis. So that's what we have down here. I can click on the drop down and I have sensitivity and optimization. So let's play with sensitivity a bit and then we'll come to optimization. So I can click on sensitivity, click on new. You can give it a name if you want to. You can click enter, then you come here. So you're going to enter what you want to be varying, right? So what we want to be varying, we want to be varying the flash temperature and we want to see the effect on profit. So let's vary flash temperature. So I specify what I want to vary. So I want to vary the, it's a block variable, and that is for the flash, and then there's a temperature, so TEMP. Now the values I want to start with, so let's say I want to start from 0 to, let's say, 500. That's fine. Have I left something out? No, I don't think I have. Oh, the number of points, so maybe I want it to have 100 points. Now I can also come to define. Now over here I'm going to define the parameter that I'm interested in. So this vary is what I want to change, define is what I want to be observing, right? So I can just come here, or define is me actually just defining other variables. So I can come here. If let's say this is something from the system, so let me just call this kill cool. I want to look at the effects of the change in temperature on the duty, right? Look for a block variable. So I'm just using this to show us something. This is not part of the question. So let me look at the effects on the duty of the cooler. Now for the duty, if we should look for duty, we have three different things that come up. Specified duty. So if you've not specified a duty and you select this, when you run the simulation, you get any results, but it wasn't something you specified. In the cooler, we specified temperature and pressure. I'm showing this to us so that if you ever run an analysis and realize that your sensitivity optimization, you're not getting any results there, you should check these parameters. Maybe the variable you are specifying or you are selecting is something that has to be specified and you haven't specified it in the block. So it's either the duty is specified, maybe you enter the value in the block and you want to see the effects on exchange, or it should be calculated. So we can click on calculated net heat duty instead, right? Usually kill calc and net duty are almost always the same, so I can just click on net duty and click on select. So I've been able to define that part. Then I can come to tabulate and then fill in the variables. Then if I should run, I'll get the option for plotting up here. So I can click on results curve, so that's at the top here, and I can just click on okay. So I'm plotting on the x-axis the temperature of the flash, and on the y-axis the duty for the cooler. So this is the graph that we would get. Now let's say we want to use a variable that is not part of the defined variables or the variables already in Aspen, something like profit. Then we need to code it in Fortran. So I'll click on the Fortran tab. I'll leave a little bit of space. So with Fortran, usually we leave a little bit of space, and then I can now code it in. So let's code it in. The coding we'll do here will apply it for the optimization itself. So let's code it in. We have P prod, the value is 1.2. So let me type that in. So I can say P underscore prod is equal to, we can give it any name we want actually, 1.2. We have C cooler. So I have C cooler, that is equal to 10 to the power minus 4, so 10e minus 4. I have Benz P. Oh, okay, sure. So I need to specify Benz P. That one is already something in there. So under the define tab, I would specify Benz P. So I'll click on new. Benz P is the flow rate of benzene in the product stream. So let me just call this Benz P. Unfortunately, I can't use lowercase letters here and underscores, so I just have to type it this way. So Benz P. And for Benz P, this one is going to be a stream variable, right? It's the value of something from a stream, the product stream. So I'll click on streams. I'll come here. What I'm looking for is a mole flow. Was it mole or mass? It was mass flow. And then I'm looking at stream, the product stream, and the component I'm looking for is benzene. So benzene in the product stream. Then the other thing we also need to specify is the cooling juices. We've already specified that, so we don't have an issue. We've already specified that earlier. So let me see how I labeled it. Kill cool and Benz P. Okay. So I can come back to Fortran, and then I can now type in the profit. So I can say that profit is equal to, so I will say this is prod, the P prod times Benz P. So P underscore prod times, and then it was Benz P. So I have to type it the same way. If I'm not sure of the variables I used, I can right click on variable list, and then the variables will be here. So I can even drag and drop on the Fortran. So let me move the cursor from this side. So I can even just drag and then just drop it, and then it will appear there, right? So it's P prod times Benz P minus, so minus, let me open a bracket, minus C cooler, so C underscore cooler, the same way I typed it, times kill cooler. So this is the absolute value, so ABS then kill cool. Okay, so this is how it's going to be. So now we specify the profit, we defined the profit. So I can come back to tabulate, and then I can, let me get rid of this one. I don't want to plot this anymore, so let me delete this. Now I can specify, just call this column 1, and then I can specify here profit the same way I typed it in Fortran. If I use an uppercase somewhere, if I use a lowercase somewhere, I'll keep it the same way. So it's the same thing that we have in Fortran. Fortran says it's not complete. Let me see. Let me see what the error is. Unbalanced parentheses. Okay. And so there's a problem with the bracketing. So let me do it this way instead. Let me say that D is equal to ABS kill cool, so that I can just replace this with D. Let me see if this one is going to work now. Yeah. So I think Aspen doesn't want you to have brackets within brackets. It can make it confusing. So this ABS kill cool, so I can just replace that with D. Now let's try running it and see. Okay, there were no errors. If we had errors, it shouldn't be a problem. So the thing about sensitivity is that it's going to run a range of values. Some of those values may introduce errors. So if your original simulation did not have errors, but your sensitivity is having errors, it shouldn't be a problem. All you need to do is from the sensitivity tab, from the navigation pane under sensitivity, you click on results, and it gives you a list of all the values. So you see the status here, you see okay. If a particular value gave an error, you see error. If a particular value gave a warning, you see warning. So that's the thing about sensitivity. So now that we are done with this, we can look at the graph as well if we want to. So I can click on results curve, plots my flash temperature against profit, and this is what we are going to be getting. Now let's try this with optimization instead of sensitivity. So let me deactivate sensitivity. So I can come to the sensitivity tab button here, right click, and then click on deactivate so that it's no longer active. Or let me activate it again. Or while I'm here, you see active over here, I can uncheck that, right? If I just want to do a case study, I can do this as well, but then it means I'm going to run a number of different cases, and that's something for another time. So I'm just going to keep it deactivated. Now I don't want to retype all of this, so let me just copy this out, use it again in the optimization. So optimization, you can click on the optimization folder here, click on new, enter the name. And for the optimization, we also have to define our variables. So things like our Benz, P and our KO cool as well, right? So we have to define the things that are already in Aspen, because you're definitely going to relate your code to something that's already in Aspen, like the flow rate of your product, the duty of the cooler, right? So I'll use the same thing so that it becomes easy to, sorry, it's a string variable, that it becomes easy to, I don't need to change the code. It's the same thing I've typed out. So this is mass flow product stream, and then it's for benzene. Then the other thing is the kill cool. So kill cool, this is a block variable. It's the, so block variable, it's for the cooler, and then it's the net, was it the net duty? Yeah, I think it was the net duty. Yes, so the calculated net duty. Yes, so that's fine. And the objectives and the constraints. So the objective is going to be the profit. I want to maximize profit, but I've not yet defined it, so I can come and define it now. So I'll come back to the Fortran and I'll just paste the code there. Yeah, I'll just paste the code there. I didn't want to type the same thing again, so I'll just paste the code there. So I want to maximize profit. Oh, Fortran is saying there's an issue. Let me see. Okay, so it's fine now. I think there were extra spaces or something. So you can type it out just to be safe, right? Now what you want to vary is the temperature of the flash. So I just click on new. I can define it as a block variable because it's a variable for a unit. That's the flash. The block is the flash. The variable is temperature. So I can enter a range of values I want. So I want to start from maybe, let's say 0 Fahrenheit to maybe 500 Fahrenheit, and I can enter a step size, so 1. So everything is done. Right, now for optimization, if I should run this, I'll see my results. But let's say we wanted to add a constraint, right? There's constraint down here, so I'll come here, click on new. You can give it any name you want. And let's say for my constraint, I want to say that the let me see. Let's say I want to run the flash so that whatever the temperature gets to, it shouldn't make the vapor fraction above a certain limit. So maybe I want to play around with the flash. Okay, let me use a flow sheet to explain something, then I can come back to see what I want to say. Now over here, if the flash temperature is very cold, right, if it's very cold, we can have a lot of products being formed, so that would increase our profit. But for it to be very cold, it means we need more utility for cooling, so that would also increase our cost. So there's a balance between how cold we want it and how much products we are going to form. But if you think about it, for you to form more products, it means you are forming less vapor. So let's say you want to set a constraint and tell Aspen that, okay, form as much product as you can. Make sure it doesn't get too cold. But we want to set a constraint, and the constraint is that we don't want the vapor fraction to be below a certain amount. There should be a certain amount of vapor still being produced, right? So that's what we want to try. It's not part of the question, but I'm showing this to us for learning purposes. So let's say we want to tell Aspen that, okay, we want to maximize profit. Profit depends on how much products we are using and the cost from how much cooling we are doing. But we also don't want the vapor amount, because if we produce more products, we can get more profit. But we don't want the amount of vapor produced to be below a certain value. So we can set that in Aspen too. So let's set that constraint. So I'll define what I want to set. So I'll call that vapor fraction. It's for a block for the flash. So I can come to block variable. I can select flash. The parameter is the vapor fraction, so I can find v fraction. Usually it's one of the last things down there. Then for the specification, I can say that I want my v frac, so my vapor fraction, to be greater than or equal to, let's say, 0.3, and the tolerance, so how much I'm going to allow for deviation, right? Then in the optimization input, under objectives and constraints, I can select that constraint. Now I can click on results here, and then I can run the simulation. Hopefully we wouldn't get errors from that. Okay, so when I'm done, Oh, the results are supposed to show. Okay, let me go back and come again. Oh, the results are not showing. Let me see. There are no values. Okay, let me quickly check what could be wrong. Profits. I think it should all be fine. Okay, let me reset and run again and see if we get something this time. Okay, that's fine. So now let's check what the error is. Okay, so there's an error with running the optimization. So let's see what the error is. It says sample. Oh, okay, I get it. Okay, so remember when I spoke earlier about variables that are calculated and variables that are specified? That's one of the issues we are facing here. So let me go back to constraints and then let me fix that. So you realize here that, let me type vapor fraction. Interesting. I think the vapor is without without the u. So vfrag is what has been specified, not what has been calculated. If I want what is calculated, I need to specify vcalc instead. So that's what I'll have to rather select. So that was where the problem was coming from. So let me call this vcalc instead. So the issue was just that, remember I said if you are running an optimization of sensitivity and you've not specified that value and you try to run it to get an error. So this is an example, right? So what I selected was a specified variable, not something that is going to be calculated by Aspen. Now let me reset and then let me run it again. Okay, there are still errors. Let's see. There's a problem with the cooler. Okay, let's see. It's not in mass balance. Sure. I think I'll take out the constraint and then we'll try that again. KO cooler has not been calculated. Has also not been calculated. Okay. So it's not doing our calculations for those ones. So let me take out the constraint so that, let me deactivate it and then let's try that again. Okay, results are available now. Let's see the results for the optimization. Still blank. Okay. Okay, let me check the inputs here once more. Okay, let's see. Let me use calc instead and see if that makes it better. Interesting, because it worked when I did it the first time. Okay, let me just check this side too. Wow. Okay, sorry about that. So one of the things I realized was the whole thing was just messing up with me. I typed out the, let me show everything. I typed out the Fortran expression again, and then I came back here. I changed this back to net duty. Yes, under the vary, I changed the step size. So with the step size, sometimes the value you enter might not be sufficient enough to help Aspen do the optimization. So you need a very small step size. So I think 0.01 is a good enough value. Using a value like 1 can create some issues, right? And then even with that, I was still having issues. So I realized it could be an issue based on the convergence. So you can come to convergence. It was solver O2, that was for the optimization. So we can come to convergence and then you can double click on Okay, I think that's for the results. There's up here, there's options, so you can click on options. You can come to default methods and you see optimization here. So under optimization, you can choose any of these methods. So if one of the optimization methods is not working well and you are having convergence issues, you can click on another. So we're using SQP earlier. Let me reset it and see if there would still be errors this time around. Yes, so there are still errors this time around, and they are saying here that the error is that there's a missing value, so it wasn't able to calculate the cooling duty before it worked, and the number of iterations also didn't favor that. So you can come up here back to convergence, come to options, change this from SQP, so we can try maybe um BBYQA. We can consider that one, then we can run it. This time we have results, and if you should check under optimization and the results are blank, right, so what you can do is you can check under the convergence as well for that particular solver. So under the convergence you have, I think it was solver O2. Oh no, that was for 22. Now it's called it solver O3. So we have the objective function value, so this is going to be the maximum profit. We have the flow rate of benzene, that would be reasonable for that, and then we have the um, cooler duty as well that we will need. Then if we should go back to the main flow sheet, we can actually check. So if I should check the stream results, it should have optimized the value for us. So now it's giving us a value of 434 Fahrenheit. That's what it's telling us would be the optimum temperature to use, right? So this is how we can go about it. You can also check for the flash as well, because it was the temperature of the flash we are interested in. So I can click on results, then I have the temperature of the flash here, 434. So that's what that's optimized. And it's saying at that 434, you would be getting a profit. Back to the convergence side, you'll be getting a profit of about 604.941975 dollars, right? We can see our manipulated variables here. So that was the temperature, that's what we're changing. So our lower bound was 0, upper bound was 500, and then we have the values here, and then the iterations, the calculations that it did. So all the calculations that it did. So I think the initial value started with was 435. I think that came from the previous optimization that was giving us some errors, right? So we have the initial values and we have all the iterations that it did until it got to the very last iteration. So this is how we can do optimization. Yes, and when it comes to sensitivity and optimization, it's very easy for errors to come up, right? So when they do, check the convergence side here, right? Try a different optimization method, and then you can view your results under the convergence um folder. And so that's it for optimization in Aspen. Okay, thank you very much.